Good afternoon. Welcome to Krishna's classroom. We continue with our discussions on the concept of connectedness. This lecture we introduce a concept called path connectedness, which is closely related to connectedness, although they are not the same. As we guess it, it amounts to the same, the following. If you have a metric space, the question that you ask is this: can you start from a position or some point in that space and walk smoothly, that is without jumping fences, to another point in the space? This is roughly the idea. Okay, and if that is possible, then you say the space is path connected. That means you can actually find a path, a smooth path from one point to the other space. I mean, that is roughly the idea, but we will make a very precise definition of this. So, how it is related to connectedness? Connectedness, as you know, is the given space can be split into two or more pieces. Okay, and that also we have specifically very precisely defined, and we introduced the notion of what is called separated sets. And can you express the space as the union of separated sets? Now this is the question that you ask. Yeah, but are they the same? If not, how much they are related to one another? These are the questions that we solve. So we begin with the definition. First, we define what is a path. Let X be metric space. A path in X is a continuous map gamma from the interval, the closed bounded interval 0, 1, 2 into X. If gamma 0 is equal to X and gamma 1 equal to Y, probably like this one. This way. If gamma 0 equal to X and gamma 1 equal to Y, then gamma is said to be a path joining X and Y. Therefore, our problem is this: Given any pair of points in X, does there exist a path? Now path we have defined precisely. We require this gamma, which is a map from the with the domain, the closed bounded interval 0, 1 to X is a continuous map. Incidentally, I will make some statement about this. We are talking about an interval of the real line. Now you know that the connected sets in R have been characterized to be intervals, any sort of interval. Here we are talking about a closed bounded interval 0, 1. And this is a connected set. And it is also, we'll say more about it as we go on, when we introduce the concept of path connected sets. If gamma 0 equal to x and gamma 1 equal to y, then gamma is said to be a path joining x and y in x. And we say that x is path connected to x. That means there exists a path connecting the points x and y, x. We look at some examples. And this is what we call path connectedness. And you talk about a path connected space would be naturally any pair of points given there is a path connecting them lying inside that space. That will be the obvious definition of a path connected space. Example. So we do some results. So remarks. The first one, if x is path connected to y, then y is path connected to this. You can go smoothly from x to y, you can return along the same path. We'll give an example. So that means x path connected. So let gamma such that continuous such that gamma 0 equal to x and gamma 1 equal to y. That means x is path connected to y. Now define, so we want to discover a path. So this is x, this is y, and this is a path. So this you call gamma, and what you want is a path from y to x. So we have to reverse the whole thing. And this is actually a map from gamma t. This is the path, and gamma is of course a continuous map. Okay. So you define one minus. Then gamma is continuous. Sorry. Sigma is defined from. See, you have another path. So this is actually coming like this. You have, see, T01 is mapped into 01 by T going to 1 minus T. So you call this some tau. Okay. Then you see that tau 0 equal to 1. This is tau 0 equal to 1 and tau 1 equal to 0. Okay. Now what one does is define a map from here to here. So put S equal to 1 minus T. So you are putting S 1 minus T. Okay. Then you define gamma S. So gamma S is gamma S is equal to 1 minus T. So gamma ST. So this is tau of T equal to S. Okay. So you first define from this, you take a point here and then define it. So you define sigma T to be gamma 1 minus S. So, or you are writing it as gamma S of T, which you call tau of T. Okay. So gamma composition tau sigma, and it's a map from see, 0 gets mapped to 1, 1 gets mapped to 2. So you are going back from here. So this point goes over here, this point goes over here through this map. Right? Therefore, consider this map. Sigma is continuous and sigma 0 is equal to gamma 1 and sigma 1 equal to gamma 0. Gamma 1 equal to y. So this is the map. So it says that there is a path from y to x. I mean, that's somewhat very simple thing. Nevertheless, I think we would need this sometime or somewhere. The problem is we do very natural things, but we have to mathematically express it properly. That's it. So the next remark is that if x is path connected to y, and y is path connected to z, then x is path connected to so this is what you have. This is your x, you have x, you have y, so you have a path gamma 1, you have a path gamma 2, then you can define a path gamma 3. Gamma 3 will be the combining these. Okay, so we will be reworking on this path, and that will be called gamma 3. So gamma 3 is going to be a path. I mark it with the red color, and so you can see how it is redefined as a map from 0 to 1, such that gamma 3 of this is gamma 3 of 0 equal to x, and gamma 3 of 1 equal to z. So gamma I from continuous such that gamma 1 0 equal to x, gamma 1 1 equal to y, gamma 2 0 equal to y, gamma 2 1 equal to z. So there are two paths. One is defined like this, the other one is defined like this. Okay. Now we have to just work out a path gamma 3. It simply says that suppose you consider a dynamic picture. You are traveling from x to y in 1 hour, and from y to z you are smoothly traveling in 1 hour. Now you want to travel from x to z along the same path smoothly in 1 hour. So what do you do? Travel twice fast on this path, and then twice fast twice fast on this path, and put them together. So you reach from x to z. And this is exactly what is happening. It's a dynamical picture. So define. It's quite easy to work it out. See, you want gamma 3 gamma 3 0 equal to x, gamma 3 half equal to y, and gamma 3 1 equal to z. This is what you have. Okay. So how to make this path? Now what we want is the following. So let gamma 3t be defined by, you have to use a gamma 1 and gamma 2. I said you travel twice fast along gamma 1 and twice fast along gamma 2. Therefore, what you have to do? This is equal to gamma 1 2t over and then gamma 2 okay, so you see that this is patched nicely, because what happens is at half gamma 1 you get gamma 1 1 and you are at y, and at half again you are at gamma 2 0. Gamma 2 0 is again y. So you are starting from y in the second lap. So in the first lap you go along gamma 1 2t, and second lap you go along gamma 2 2t minus 1. That is then continuous. Gamma 3 maps into x, gamma 3 of 0 so what it says is that if you have two paths, you can join them together, okay, and get a joint path as you have seen. So now we define what is called a path connected space. It is the theme of this lecture. A metric space X is said to be path connected if for every x comma y belonging to x there exists a path gamma from every pair of points xy belonging to x, there should be a path. Now this is important. For every xy belonging to x, there exists a path defined like this. A smooth passage from x to y, staying completely in the space. Now we shall remark an interval is path connected. See, if you take any interval and take any 2 points x and y in it, what happens? See, if I is an interval may be closed, open, or the endpoints are not there, or one endpoint is there, one other endpoint is not there, something like A, B, say, then you know that X and Y are 2 points in it. There is always a path in the space going from X to Y. I mean, that is an obvious, okay, connecting it. So what you have to do, you have to expand this sufficiently and scale it up and map to the, or you have to find a map from 0, 1 to this through scaling process. What is it? So define and see, what you know is that if there is any z that lies between x and y, and this is the property of the interval. If x and y are arbitrary points and without loss of generality assume x less than y, and if z is something, some point which lies between x and y, then z is also in I. Now this is the structural property of the interval. Now what we want to do is when you go from x to y, you can continuously travel across from x to y, traversing through every point that lies between x and y. So we define the following. This is quite easy to find out what it is. This you write as one minus dx, so that as gamma is a map from 0 to 1, write it in the form of ax plus by, and then compute a and b such that the interval line, it is gamma 1 equal to x, sorry, gamma 0 equal to x, and gamma 1 and in between for values t which lies between 0 and 1, you get intermediate points between x and y. So this is what you have. For t belonging to, and this is a smooth function and gamma is continuous. So there exists a continuous map from 0, 1 into the interval AB such that gamma 0 equal to x for any given any pair of points x and y in AB, say x less than y, gamma we can write the function as gamma t equal to ty plus 1 minus tx, and which has the property that gamma 0 equal to x and gamma 1 equal to, and gamma t lies between x and y for all t belongs to x. That means when you travel over the interval 0 to 1, the corresponding image gamma t will be traveling from x to smoothly. That's important. Okay. Now you see that this is something to be observed. To the second remark, the set is not path connected. Why it is not path connected? The reason is this. See, suppose then there exists a continuous function choose x to be minus half and y to be half, or any point x in this part, or for that matter x belonging to minus 1 to 0 and y belonging to 0 1. Okay, but I am making some specific choice. Then suppose you have a path like this. So gamma t is a path. Gamma t gamma is assumed to be continuous. That gamma t equal to 0 for some t why it is so? Because you see that gamma is a continuous function. Gamma is a continuous function from 0 1 to this interval. So you have gamma 0 is minus half and gamma 1 is half, and therefore see by the intermediate value theorem there exists a t such that gamma t 0. Simply says this. See, suppose you have this is the interval 0 to 1. Now here we are making a map from minus half to plus half. Okay. So it's something that starts from here. The graph will be starting from here and probably ending somewhere. This is your half. This is your minus half. And you see that there is some t in between because it's a continuous function. It has to cross this line to get there, go from minus half to plus half. Okay. So there is some t for which gamma t equal to 0. So this set is not path connected, it's not even connected. So this is a contradiction. But 0 does not belong to the set so that's a contradiction. So if you have any continuous function, then it has to attain the value 0 for some t that lies between 0 and 1, but this 0 is not in your range space. Therefore, this is not correct. That's an example of a path connection. It's a very simple one. If you take any disjoint intervals, put them together, it is going to be a space which is not path connected. Obvious. That's what I was telling. We will have to jump across from one part of the one component of the space to another. Now, third one is that, say, Rn is connected. Now that's clear. Suppose you take x belonging to Rn, y belonging to Rn. These are two vectors in Rn. Now consider the function gamma from defined by gamma t equal to ty 1 minus dx. It's a linear combination of the two vectors x and y with coefficients t and 1 minus t. Now it's continuous. Rn is the usual metric space. Rn, we are talking about that. So gamma is continuous. And gamma this is actually the following. Let us take R2. So you have two vectors x, this is x, the vector x, and this is the vector y. Now what we are talking about is this path. Starting from here to go over here. So all the intermediate points are described by this. Okay. So this will give you the corresponding map. So Rn is path connected. Now the fourth statement is any convex set in a normed linear space is path connected. What do we mean by a convex subset in a normed linear space? So if X is a normed linear space, and suppose you Consider the set E. Now E is said to be convex if X and Y belonging to E, XY, so E is convex if X, Y belonging to E implies belongs to E. That means all the points that lie on the line joining X and Y belong to E. And this is one of the points that you have. So this you call gamma. So define gamma t equal to Ty plus 1 minus t x for t belonging to 0. Then you have it's continuous, and gamma 0 equal to x and gamma 1 y. Now you see, this is an example of a convex set. Now suppose you have a set like this. I want to make a remark. So the natural question might come, oh, okay, it's fine. When you have a convex set in a normal linear space, it is path connected. But are they the only sets which are path connected? Yes. So there are questions like this. Suppose you have a set in R2 you take. Suppose you have a set like this. This is not convex, but is it path connected? I mean, clearly you can see that your common sense tells that you can define a path from here to this way. This point. Although between X and Y, you don't have a straight line connected. This is not there. Okay. But this path is always there. Okay. So we have to account for such spaces also. So all this, the above result that we have proved says that there are linear paths from, or you can walk straight from X to Y without any hindrance. Okay, that will give you a continuous path from X to Y space without trespassing the boundary of the set once it is convex. If it is not convex, then you'll have to find other ways. So the question that you ask is, that's a question that's asked. The answer to this is no. That is the answer. So we shall say more about this because suppose you take R2 and remove the unit disk from it. Is the leftover path connected? For instance, if I take a point here and a point here, I do not have a straight line path joining X and Y. But certainly I have some path like this which connects this X. But how to show that there exists such paths? in a general matrix space we work. Okay. So let us, the following lemma conclusively tells you what to do. Let be arbitrary. Let alpha and beta be paths joining A to X and A to Y, where A is a point a fixed point. Okay. So we have two paths, alpha and beta, joining A to X and A to Y. Let sigma be the reverse path joining X to A. Then there exists a path the point is this. Suppose X is a point, Y is a point, A is a point. Now suppose this is the path alpha and this is the path beta. No, sorry. This is the path. This is the path alpha. Is from A to X, and the path beta is from A to Y. Then you are talking about a path from X to Y, combining these two. What do you have to do? You have to go through the reverse path from X to A. There is no hindrance because we already gone the other way around. And there is the corresponding path beta from A to Y. So first go to A along the path alpha, and then the reverse path alpha, and then go along beta to reach Y. So that's easy to do. A path and beta I think I stated the lemma wrongly. I will write the lemma properly. Okay. What I wanted to prove was this. Sorry. I'll wipe it off. I have written the proof of this here. Okay. So the statement of the theorem is this. A metric space X is path connected if and only if there exists A belonging to X which is path connected to this is what we want. A metric space X is path connected if there exists a point A belonging to X which is path connected to any X belonging to X. So what we want to do is choose some arbitrary points X and Y in the space and then show that there is a path joining X and Y in this space. So what is known? So let us prove this lemma. Okay, so let us systematically build that. Assume that there exists A belonging to X such that every element of X is path connected to so let xy be now arbitrary points and alpha be a path joining A to X and beta be a path joining A to Y. Okay. Let sigma be the reverse path joining X to A. Then what do you have? So this is the path A to X is given by alpha and you have sigma which goes in this direction. In this way, so color coding, sigma is this path. Okay. That is the reverse path. Then what is the path that you have? The path that you have is use these two things together. Okay. Then see you have two paths, one connecting X to A and the other one connecting A to Y. Now you can use the previous. Then sigma connects X to A and beta connects A to Y. Now you can use, if you have to such thing, earlier we have said that if you have two paths, gamma 1 and gamma 2 connecting X to Y and Y to Z, then there is a path that you can concoct from that in the using these two maps. So as we have computed already, gamma connecting X to Y, and if you want you can define it clearly. The path gamma can be precisely given, and I will give it here. So you have got gamma T equal to sigma 2t minus 1. No? And for 0 less than or t less than or equal to 5, and this is beta one, because you observe that gamma half equal to beta half, which is equal to. So that is the precise definition, the definition of this. So that is one part. What we have proved is this implication. Suppose there exists such a path, then this. Conversely, that means we will prove in this direction. If X is path connect, then choose any point A belonging to X. Then X A is path connected to any point in X. So you get this what is called this alpha and okay. So that completes the proof. Now, one example disregard is now you see that the annulus is connected. No, I think I'll take up this problem later. What I want to do is this. Yeah. See, this one is not path connect. Sorry. 0, 1, 1, 2 is not path connect. This we have already seen. Now what happens is that, okay, suppose you take any point here, it cannot be connected to any point here and vice versa. Okay. Therefore, if you see, we show that this result does not hold. There does not exist A belonging to 1, 2 is path connected to every x belonging to 0. Sorry, 1, 2. Why? Suppose, see, if there exists such an A, then A belongs to 0, 1 or 1, 2. Okay. So if A belongs to 0, 1, then it is not connected to any point because it has to trespass 1, which is not there. So this point is missing from that. So it has to trespass 1 to go from here. To go from here, it has to trespass this particular. That's the reason for it. Therefore, it is not path connected. Similar argument holds if we assume A belongs to what? There does not exist A belonging to the set one two such that A is connected to every point in this space. So that's a situation where it does not happen. And incidentally, is not connected. It's not connected. So it is not path connected, it is also not connected. Okay, so that we shall keep it in our mind. Now suppose you take now we shall make an observation that so this is the result. Is path connected? Before we prove this, what happens? So for n equal to 1, R1 slash 0 is equal to minus infinity to 0 union infinity. This is not path connected. also is not connected. Now this we have already seen. Okay. Now we try to prove this. Therefore, this is the case where n equal to 1. So for n equal to n greater than or equal to, let's see how we work. First, let us try to solve this problem geometrically. So we shall prove the following. So in Rn, consider the E1 and E2, where E1 is 0, now in R2, this is E1, this is the vector E2. Now what we want to assert is the following. Okay. Consider X E1, the line joining X with E1, and Y E2. So X is some vector, Y is some other vector. So this is X E1, this is this is Y, or rather X E2 is this is X. For some X, then at least one of them, see, this stands for that is a notation. Therefore, at least one of them, namely say X E1 or X E2, does not contain 0. Sometimes, none of them contain 0. For instance, if your X is somewhere here, say, then X E1 contains 0. But in that case, X E2 will not contain 0. Okay, so if you take X here, then X E1 contains 0. But X E2 does not contain 0. I will mark it. Okay. So one of them, maybe both. Suppose this is not true. Then 1 minus t x plus tx equal to 0. Okay. Sorry. That is what does this mean? This means, and t of course belongs to 0, 1. T is not equal to 0. Therefore, what is that you have? You have 1 minus t e1 equal to minus tx. Okay. Suppose this is not true, then this is so, and you have, and there exists such that 1 minus s into e2 plus sy or sx 0. So you have 1 minus s e2 equal to minus 6. Therefore, since s is not equal to 0, t is not equal to 0, we have which implies for and that would mean that E1 and E2 are multiples of x. I would say scalar multiples. And this is impossible. Not possible. Because E1 and E2 are linearly. So that's a contradiction. Okay. So at least one of the lines E1 x and E to x do not contain the particular the point 0. Now we'll continue with it, and then we examine the relationship between connectedness and path connectedness. That's our next task. So thank you very much.